All right, we're going to do a simple proof of a theorem that you usually see when you learn about irreducible polynomials or irreducibility over k adjoint t. When you have a ring, it's not quite the same. In particular, I'm not making any UFD claims or anything like that. But anyways, any non-zero polynomial over a subring R of C is a product of irreducible polynomials over R. Again, not making any unique claims here. Just you can write it as a product of irreducible ones. So proof, we induct on the degree of G, where G is our polynomial. That's the degree symbol. If the degree of G is 0 or 1, there's not really anything to do. It's constant, so it's automatically irreducible. If it's degree 1, it's a linear, it's automatically irreducible. So suppose the degree of G is bigger than one of these. If G is irreducible, we are done, because you can write it as itself. Otherwise, it's not irreducible. The opposite of being irreducible is being reducible. So we can write G as a product, write G as H times K, where the degree of H and the degree of K are strictly less than the degree of G. By induction, H is a product of irreducibles. K is another product of irreducibles. And so, G, which is H times K, is a product of irreducibles times a product of irreducibles. It's just a bigger product of irreducibles. And lastly, I also want to point out that I made it pretty clear that we're not claiming any uniqueness of this factorization. This is purely just you can write it as a product of irreducibles. That with irreducible properly defined and us taking that into consideration, there is not in general going to be unique factorization. So you can write it as a product of irreducibles, but that factorization need not be unique. There are rings, subrings of C, namely like Z adjoint square root -5, where you don't get unique factorization in the ring, so you're not going to get unique factorization in polynomials over that ring. So let me just caution you, let me just, say here that we're not making no claims. I guess that was the end of the proof about unique factorization. Only that it exists. And in the context where we're going to care about factorization is maybe another star. We'll care about this when R is actually a field, in which case you do get unique factorization. Where we won't have to worry about any of this. Should we need uniqueness, we'll restrict ourselves to fields where that, of course, is true.